So we're going to talk a little bit about statistical modeling, basically filtering and smoothing of data, with focus on resilience trajectories, but very much from a biologist perspective and from an old school biologist perspective. So if you were expecting 40 minutes on machine learning and deep neural networks, you should go next door. I don't know what they're teaching in there, but you won't hear it here. So. Okay. So for those who don't know me, I'm Nick Friggens. I work in this unit in INRAE called MOSAR, which stands for Systemic Modeling Applied to Ruminants. And our research animal, as you can see, is the dairy goat. So we fit comfortably in smarter. So we'll work our way through gaining insight, biological insight from time series data. If we want to do that, we need to think about the ease of use of our statistical models relative to their biological meaning, getting the biological signal out from the noise, filtering, smoothing resilience data, and then a little bit about validation, because it's very easy to do lots of things with data, but in the end you need to show they actually mean what you think they mean. And a very, very quick part about how you can combine time series measures, and then we'll wrap up. So quite a bit of stuff to get through, but all of that is really already available. If you want to find out the technicalities of fitting a particular function, you can go and look for all the help on the R forums. You can use Wikipedia for the formulas and everything. So I'm not going to spend a lot of time digging into all of that. I'm going to take some advice from a colleague who, when we were putting together a talk like this some years ago, said, well, these theoretical presentations, they actually ignore the kind of real-life problems that you get to. So don't spend time on the statistical issues, it's the biological focus and your practical experience. And that suits me very well. But just to start off with, I think it's worth going back and thinking how lucky we are. We have precision livestock data for lots of things. We have time series data. Most cases out on real farms and in the past when you were doing research looked like this. And I'm not sure why I'm missing. I'm okay, yeah. A lot of blank space. So this is a graph for a particular cow through lactation. And this is where the farmer thought he saw something going on. He was looking for reproductive behavior. So the pink triangles are where he thought he saw indications of reproductive behavior. And based on that, he attempted to inseminate the cow at these points with the red arrows. But the thing is, on this graph, there's really very little information. You're really in the dark. If you have repeated measurements, you get a much, much clearer picture. So the very fact that we have time series allows us to get a lot more information out of our data. These are progesterone measurements made in milk. The blue dots are the raw data, and the blue line is a first attempt at smoothing. So, why are we lagging behind? Okay. So we're not going to talk about the statistical methods. We're going to focus on the gaining of the biological insight. So what I've chosen to do is put up lots of graphs like this with lots of different examples. And the idea is that this is interactive. You don't just listen to me for 40 minutes. That's painful. If you have questions, if there are things about these graphs that you want to know more about, please ask in at any time during the talk. And so far, you've all been very quiet, both yesterday and today. So now's your chance, okay? But so far, this is just a time series of data with some smoothing. At the moment, there's no biological insight. There's no interpretation. And this is coming back to things that Masoud was saying before. If you have a particular problem, it's not enough to just have the data. You also need to have an idea of what it is you want to get out. And we can do that in lots of different ways. So one example of putting biological interpretation is this. So these symbols on the graph represent different biological states for the animal, different reproductive states. The black crosses here, they're saying that the animal is at the start of lactation, she's in anestrus. The red stars, she's estrus cycling. And the green diamonds, and apologies for those of you who are colorblind, the green diamonds are she could be potentially pregnant. And all of that is based on a very simple rule, and you can see it here. We simply said there's a threshold, and every time the animal crosses that threshold, that changes her status. And that's because we know something about the biology. We know something about how progesterone works. So these are what's called luteal phases. This is the follicular phase. This is where the ovulation happens. That's one way of interpreting the data. And if you look at that as a model, you can see how that fits together. Over here we have our signal. This is the smoothing part, so that's the difference between the blue dots and the blue line. And then the symbols, they come from mixing that with some biological information about the fact that when cows are newly calved, they start off in postpartum anestrus. Then they can shift to estrus cycling when they come up above that threshold. They dip down again, that's estrus, and they can be potentially pregnant, but obviously if they're not inseminated or the insemination fails, they come back round again. So that's one way of looking at that information. And what's interesting is when you put some biology on, you can now have a range of different outputs that you can predict, which you couldn't do beforehand because you didn't know where you were in terms of the reproductive status of the animal. But we can do this in other ways. Instead of putting something based on a threshold like that, we can smooth our data in a different way. So I'm going to show you an example of smoothing data using a dynamic linear model. Sorry, that was a dynamic linear model. This is smoothing with something called functional data analysis. And that's something we'll come back to later on because in the exercise part, you can play around with some R code to fit this kind of analysis. So the red line is a spline function with some details. We'll come back to those. What's interesting is that even though this is a purely statistical method, that method allows us very easily to identify where the curve changes. So you can see it rises and then it drops again. In other words, where the velocity of that curve is going through zero. And we can do the same for the acceleration. And we can pick out features using that. We can calculate the length of a cycle. We can calculate the amplitudes. We can look at when progesterone is rising fastest, when it's dropping, so on. So that's another way of interpreting the same data. And you can put that information for a large number of animals, these features, the rate at which it drops, the rate at which it increases, whether the cycle is longer or shorter than average, do some multivariate analysis. And what's interesting here is we generate some hypotheses now. We now say, well, cycles differentiate themselves in two different ways. It can be something about the length of the cycle. It can be something about these other features. And then we can go a step further and say, well, does that predict anything? So it's just an example of different ways of approaching essentially the same data. And it depends on the question you're asking. Are you wanting to detect estrus, in which case we use the first system? Are we beginning to look at what kinds of shapes of estrus cycle are good for a cow getting pregnant? Then this might be a better approach. But always, here we've just used the same data. Everyone's very quiet. Generally speaking, with time series data, I would say the more measures you have, the more frequent the measures, the better. That gives you better possibilities of dealing with the noise. You can see that here. These are body weight data for cows that are weighed every time they're milked. And body weight, if you weigh a cow 10 times during a day, you'll see fluctuations in the weight of that cow because the cow has a rumen, and that rumen fills and empties. It has a mammary gland that fills and empties. You can see that here. So each of these points is one estimate taken from a cow standing on a weigh platform while she was being milked in the milking robot. And this is that curve. So this is seconds. This is the weight of the animal. So she stepped onto the weigh plate. You can see there's a lot of noise because they don't jump on the weigh plate, land 4 feet at once. They arrive like this. They lean against the bars. They do all kinds of things. Kind of stabilizes. And then she's milked. And you can actually see the weight of the milk disappearing. So if you have that level of data, you can get a weight of the cow minus her milk. So you've already corrected some of the noise. Then, with these frequent measurements, you can also smooth those as well to get rid of that daily variation. And the idea here is to get at the underlying change in body weight of the animal through lactation. So the more data, the better from that perspective. Yesterday, Ellie talked about measuring feed intake, and Nicola showed the data from the feeding systems in Scotland. This is data from our feeding system. So we have a system where the goat has access to an individual bin. That bin is on a weigh cell, and the weight of that weigh cell is recorded every 2 seconds. And when you've cleaned that up, got rid of the noise when the goat is making the bin bounce around, what you end up with is these kind of data. So the black dots represents when feed was distributed. The red dots are the amount of feed that was in that bin at the time where the distribution was made. And these blue kind of curtain graphs, this is the pattern of intake of the animal through the day. Now if I can zoom in and look at one single animal, you can see the feeding behavior of that animal as you move through the day. If we have that, we can start to ask questions about how does the feeding behavior relate to efficiency, for example. That was something that came up yesterday. Or relate to methane emissions, the rate at which food is coming into the rumen, the rate at which the bugs are processing. There are lots of things we could get out because we have a lot more data. There is, of course, a downside. The more data you have, the more statistical processing you have to do. The more you have to try and find the wood from the trees, the estrus in amongst all the activity measurements. And clearly when you see something like this, it's very hard to see a pattern, other than the fact that the system was broken here. So we've seen that the more frequent the measures, the better, assuming we can handle that. How we handle it, there are a couple of things we need to think about. There's a trade-off. There are very easy to use ways of smoothing data and filtering data. They don't always have that much biological meaning. So you need to decide what it is you want to get out of your data. And then what we're really looking for is a kind of synergy, choosing the statistical models that combine best with the biological perspectives. So if you think back to the progesterone, if my question was estrus detection, I'll do it one way. If my question was, what are the features of the estrus cycle that I'm interested in, I'll do it another way. Let's talk a little bit about ease of use versus biological meaning. This is an example of smoothing of milk yield curves for two groups of animals using polynomials. So you say milk yield equals a constant plus days in milk, time plus days in milk squared, all of that. That's extremely easy. In R, you can do that you can even do it in Excel. You can smack that through. We get a reasonably good fit on average, and in this case, it's actually used random regression, so we get a curve out for each individual animal. Very easy to use, but if I ask the question, how does this curve differ from that curve? Can we answer that question easily? No. If we look at the coefficients from those models, they're here. So intercept, first, second, third, fourth, fifth order polynomial. For the low line and the high line, we have some numbers. We can use those to redraw the curves. But to say how they differ, not very easy. The biological interpretation is not easy. I'm not saying we shouldn't do this. I'm saying this can be an excellent thing to do if you want to show how, for example, individuals vary relative to the population mean. But the biological interpretation is difficult. Here's another model, which I think is a very nice biological explanation of a lactation curve. So you have a scalar. Sorry, I should say this is one of 3 equations in this talk, so there are only 2 left after this. You don't need to worry. This function u here is actually a growth function. So if you think about the way lactation happens and you think about a lactation curve, at the beginning, the mammary gland is developing, the cells are, I've forgotten the word, but it's all developing. There's a better word than that, but never mind. So there's a kind of growth of the capacity of the animal to produce milk. And then there is a kind of decay off as the system ages, as you have apoptosis and things like that. And those 2 things are explicitly represented in this model. But this is in no way linear. So if you want to fit this, you have to deal with nonlinear fitting. And nonlinear fitting, yep.
So how would you biologically define these parameters for the other one? Can we do it? Can we have the biological definition for the coefficients?
Yes, I can, and I'll come to that in the next click. But thank you for the question. So yeah, this is a pain to fit, because although there are functions for nonlinear fitting, they always are dependent on your starting variables, so you tend to have to do some kind of grid search to make sure that you end up with the best possible set of values. You don't end up in a nonlinear, in a local minimum, and so on. But you can fit very nicely. These are residuals from a curve fit, and you can see there's nothing to worry about there. And we can get out the coefficients. So A was the scalar, C is to do with the decay, it's the rate of decay of the lactation curve. G naught and B are the elements of the growth curve, the growth part. And these are a slightly different data set. Here we were looking at 3 different parities, and you can immediately see that parity affects the rate of decay of the lactation curve. So as you move from first to second to third parity, the rate at which animals drop off, so their persistency, decreases. That was significant. Not surprisingly, the scale is also affected. Older animals produce more milk than first lactation cows. But interestingly, the way in which the system grows, there was no significant effect. So we paid a cost in fitting, but we get a clearer answer if we ask the question, how does it differ between parities? So you have to think about, where do we go in that trade-off? And just to take that example 1 stage further, I don't know if any of you spent time looking at lactation curve data for cows or goats or chickens. You can do this with chickens, actually, egg production curves. And you're probably thinking, why didn't he use a Woods function? You were thinking that, weren't you? Yeah. Yes, you were thinking that. Why didn't he use a Woods function? It's not that different from this. Woods function looks like this. Here's that same decay part of the model. The scalar is there. Woods function simply uses t to the b, so a power function, instead of where I had that double exponential growth curve. So it's pretty close. It's linear in log form, so you can fit this without mucking around with nonlinear fitting. It's a very robust model, generally gives a good fit. But it's a different place on that continuum between ease of use and interpretation. Fits very well. So the pink curve here is the Woods function fitted to this lactation data, and the blue is the one I showed you before with the growth curve. Can't really distinguish between them. in those terms. Where they are different is in terms of their biological interpretability. The model with the U, with the growth function, I like because that growth function at a certain point plateaus off at 1. So it becomes neutral. So everything to do with the decay is captured in this gamma decay. The Woods function, that t to the b, describes the growth part, but it goes on increasing. So the persistency of the animal is now described not just by one part of the equation, but by the combination of these two. So it's a slightly different place on that continuum between ease of use and interpretability. It can be very useful, but it's just to give an example of it depends where you want to be. Okay. So I've tried to find some examples where we can talk about how the biological perspective may change a little bit what you do statistically. And of course I've taken an example which I had beforehand. So we saw this graph. Now let's go back. The example I've chosen is to do with energy balance. How many of you have to deal with calculating energy balance in your daily work? Yep, good. How many of you are dealing with residual feed intake and efficiency? Okay, so it's the same equation, just moved around, yes? So energy balance is important, at least in dairy cows, because cows which have a negative energy balance, there are consequences. What kind of consequences? Yeah, and what does that do to the animal?
They reduce the bone reserves, then they can develop ketosis and other diseases.
Yeah, so they can develop health problems, they can have trouble reproducing. We'd really like to know energy balance, because if we knew it, we could do something about these problems. So how do we calculate energy balance? Somebody else? How do we calculate energy balance? Yep.
If we know the intake, depending on, if we know the intake, it's the intake less the output, and the output we take into account the energy given to the lactation, the growth, and the maintenance.
Yep. Exactly. So it is what it says. It's the balance between the energy going into the animal and the energy coming out. So the energy in the intake, the output in the milk, the output in maintenance, the output in growth, and so on. Exactly. So to calculate an energy balance that way, we need all of those things. We need the intake of the animal, we need its production, we need its weight, and so on, which is exactly the same as the RFI equation. We have the intake on one side, we have the milk, we have the body, we have the composition, and so on. Yes? And that's fine. That's a perfectly correct way to do things. But that's the accounting way of looking at energy balance. That's saying, quite rightly, that energy cannot be created or destroyed. So if we calculate what's gone in and we calculate what's come out, we have the difference. Biologically, what is that difference? And this is, you actually said that. When a cow is in negative energy balance, she is mobilizing body reserves. That difference is coming from her body reserves. When the cow is in positive energy balance, she's gaining body reserves. So energy balance from a biological perspective is changes in body reserves. So if energy balance is changes in body reserves, how can we measure directly, or more directly, changes in body reserves? The body condition score, the change in the weight of the body reserves. Yep, exactly. So we take something that traditionally we've calculated using an accounting view of the world. We try and think about it from a biological perspective. That changes perhaps the way we go and get an estimate of energy balance. So here's that graph of body weight that you saw before. Because we have lots of data, we can smooth it. We now have the change in the body mass. If we have some condition score measures associated with this, we can actually calculate the energy balance of the cow directly from the changes in body weight and the changes in body condition. This is now something which we're seeing more and more in dairy cattle. People are putting in weigh crates on the way out of the milking parlour, so you have lots of information. De Laval have commercialized a camera-based automated body condition scoring, so we can have the equivalent time series in body condition score. So instead of having to measure intake, and the only people who measure intake are nerdy scientists in research centers, we could actually get energy balance on farms. Sorry, I just called you a nerdy scientist. I apologize. I'm one too. We could actually get energy balance on real farms. Now, this is slightly oversimplifying. There are some issues with doing this, but nonetheless, thinking about the biology changes the way we approach which data we use and how we use it. So, careful consideration of the biological purpose is important, and careful consideration of the interpretation you want. Those two things will guide you as to what it is and how you're going to approach your problem. Now, that was a summary. That's the good news. The bad news, it was only the first part. So, are there any questions so far? Any comments? Everybody is awake. Most of you. Ozzy, can you just move? Yeah, okay, you are awake. Thank you. Okay, everyone's happy so far? Good. Let's carry on then. And I have no idea what the time is. Oh, I'm going to go on for hours. What do we want as biologists? We want to sort the wood from the trees. We want the biological signal from the noise. So here we have an example of a biological signal. And here's one way of fitting a trend. And then we can see what's left here. But what signal are we interested in? And what is noise? We'll come back to that in a second. Are we interested in having the long-term time trend? Are we actually interested in looking in the shorter-term time trends, so in what's left, to see if there's something meaningful? There's no right answer to that question. It will depend on what your particular purpose is. Pardon?
Your objective.
Exactly, yes. Your objective, yes. And the same applies to noise. Because, okay, noise, we all think about random error, measurement error, recording error, all kinds of things, yep. But there's also interference from the environment. And I've said, for it to be noise, it has to be interference from the environment that we're not interested in, non-interesting. So if you're interested in, I don't know, how a food affects the efficiency of milk production, and then for 3 days there is a weather event, that's an environmental interference, but you're not actually interested in it, so you want to get rid of it. On the other hand, if you're interested in how cows cope with a weather event, then it's not noise, it's something you want to capture. And it's the same with the biology. Cows do lots of things, goats, you do even more things, social interactions and everything, and they may be just noise as far as your main purpose is, but they may not. And the interesting thing in this example, which we'll come back to at the end, is that this fitting here was to get at what was going on in the short-term time trends. Because this person, Marika Popper, was interested in looking at resilience. And in this course, resilience is, of course, the center of things, and it's usually in the short-term time trends. And if you want to get at that, in some way you have to deal with the long-term trends. Okay? So we were looking at this graph at the beginning and saying, oh my God, what do we do with these activity data? You can actually do lots of things. You can fit, these are already not raw data, these are already processed data. I think these are every 10 minutes or something, bins. We can put a rolling average through that. That's a very useful tool. Rolling average, rolling median's even better, but rolling average. Then we get something like this. And we can see that there are things going on in daily patterns. So we could express that, for example, relative to a 24-hour mean. And then we get something like this. And then we can put in some kind of threshold saying, well, if the activity is 40% above the 24-hour mean, then it becomes interesting. And this actually is the basis for accelerometers to detect estrus behavior. There are variants of how you do it, but it's along those lines. But remember what we said about lots of other biological things going on. We could be interested in estrus behavior. We could also be interested in the total activity of the animal. If an animal is sick, we could imagine that her activity levels change dramatically. So we can think about other ways of smoothing. And here's one example from work of Ines Adriens. So up here you see 3 different traces of daily activity. And basically what's happened is they are smoothed with longer or shorter windows. So the yellow one has a very long window. And you can see here, for example, activity drops. But because it's measured over a broader range, the yellow line stays flat. The orange one is intermediate, and the blue one is much closer to the real data. So now we're doing smoothing of the same data, but with different penalties, different smoothness. And this is something we'll keep coming back. So the short-term time trend is excellent for picking up the estrus behavior. But if you're interested in when the animal drops off because maybe it's sick or there's a resilience event happening, well, what's more interesting is the difference between the yellow and the orange, and that's what's shown down here. And that idea of differential smoothing is, for me, one of the keys of getting into resilience data. And then 2, for me, incredibly important points when you approach your data. As we've just seen with those accelerometer data, there are several different biological phenomena included in that data set. So it is likely that any given measure contains information about several biological phenomena. So we want to think about filtering and smoothing to capture the one which is important to us. And I said especially differential smoothing. And the mirror image of that first statement is, it is rare that one single measure will capture all of the different elements of a particular biological phenomenon. So if you think about something like mastitis, mastitis often causes a drop in milk yield. But that doesn't tell us anything necessarily about how inflamed the udder is. So what might we look at for that? Somatic cell counts. So that's a different facet of mastitis. If mastitis is particularly bad, it also affects the junctions between the cells, so the blood-milk barrier. So that's another measure. That you won't get that from somatic cell count. You get that perhaps from conductivity. So if we want to fully capture mastitis in all its elements, we perhaps need to look at multiple measures and extract from each of those features, which we can then combine. And at the very end of the talk, we can come back and I'll have an example from mastitis. Yes?
Quick question. But sometimes people use standard deviations to throw away data. If you did that, you would lose some of those peaks.
Yes. I totally agree. So you're saying if I used the standard deviation, I would get rid of those peaks? Yes.
Yeah.
Yep.
In that case, you'll be losing good data.
If you're interested in estrus behavior, yes, that would be a bad strategy. If you're not interested in estrus behavior, then it can be a useful strategy. But that's an extremely good point, yes. So how do we filter data? You've all played with data sets, I imagine. What kind of things do you do when you start looking at data? What's the very first thing you do? Pardon?
Normality checks.
Okay, normality checks.
Checking for outliers. But that's
What's an outlier?
something that goes beyond than, say, the average of your data.
Yeah. Yeah, if it's body weight data, the cow we know doesn't weigh 100 kilos.
But that needs to have a biological meaning.
Yep, exactly, exactly.
The other way is to say why filter in the first place. If you can answer that, then the rest will be why do you need to filter?
You need to filter because reality. If measurements were perfect, we wouldn't need to filter, but I agree.
No, I know. I'm just saying that I'm putting it upside down.
Yep. Yeah, no, that's good. That's good. And I think everybody has graphed their data. And although it's funny, at some point people start to skip that step. They start to say, oh, I know I can go and write some code, and whoa, I love writing code, and I'm going to make a super duper filter, and then, whoom, and then come back and look at the graphs, because, yeah. And then, of course, we can do lots of things. A useful technique, although Ozzy has just warned us of the dangers, is to use residuals as a way of getting an idea of what you think is good or bad data. And to do that, we start smoothing. So rolling average is very useful for time series data. I'm getting more and more enthusiastic about the rolling median because it is less affected by the extreme values. But there are lots of other methods. There are lowest regression methods, which is a local regression, splines, and so on. This is an example with splines, and it's doing exactly what you were saying. So we fit a spline curve through this lactation curve data. Interestingly, if you fit a Woods curve through this, it would have a different shape. It would be difficult to deal with this. The idea of setting a threshold to say any milk yield under a certain level is going to be a problem, because if you set the threshold here, because we want to capture these 2 points, we're going to run into trouble over here. So we need to do something a little more sophisticated. So yes, typically what you do is you say, we have the residuals, we can calculate the standard deviation, and we set some boundaries. And that's pretty effective. The question is, are these points that you're interested in or not? And that only you can answer. And what we're doing is we're smoothing a time series in order to filter it. So in a sense, and this comes a little bit back to what you said, why filter at all? If our smoothing is working well, then maybe the filtering is done implicitly within the smoothing. But I did want to draw your attention to another way of filtering data, which I find very useful. These kind of methods, you normally need to have all of your data. So you're kind of doing a historical thing. The data's all there. I'm now trying to get rid of some outliers because they're a pain in the ass for what I'm doing afterwards. Often, things are moving day by day, and you want to keep an eye on what's going on because you want to be able to say, well, there's a problem now, we need to go and change something on the farm. And the other way of doing it is to transpose your data. So when you have lots of animals, you can start to say, I will compare yesterday's value against today's value. And for most things, body weight, milk yield, so on, we expect today's value to be pretty damn close to yesterday's. So if I have enough animals, I can do a simple linear regression, day by day, through my data set. And I'm filtering in a way that's independent of the time series analysis I will then do later on. And then, of course, I have my regression, and I put some boundaries on. They don't need to be symmetrical. They can be. But often, we have a good idea about where we expect deviations. I expect cows to drop in milk yield from time to time because they haven't had food or because they're ill or whatever. I don't expect them to suddenly double their milk production. If they do that, I'm pretty sure that's an error. So I can be a little bit harder on the positive side than on the negative side. So we've managed to talk about filtering and smoothing without actually having one single equation. So that's good. Questions?